There's a place in northern Kenya where you can stand on solid ground, and, according to the geologists who study it, be standing on what will one day be the floor of a brand new ocean. Not metaphorically, not in some abstract, deep-time sense that only matters to a textbook. Actual physical seafloor, forming right now, slowly enough that nobody alive will ever see the water arrive, but fast enough that scientists have recently had to throw out their previous timeline and write a considerably shorter one. Africa is splitting in two. That's not speculative or exaggerated. It's the settled conclusion of decades of geological research. And in 2025, a study published in the journal Nature Communications found that the specific stretch of crust most likely to break first has progressed much further along in that process than anyone had previously realized. This is the actual current science behind Earth's newest ocean, one that's quietly forming underneath one of the most geologically active landscapes on the planet. Most people think of Africa as sitting on a single, unified tectonic plate. For the vast majority of the continent, that's essentially true. But in the east, the picture is considerably more complicated, and that complication is exactly what's driving this entire story. Running from the Red Sea and the Gulf of Aden in the north down through Ethiopia, Kenya, Tanzania, and into Mozambique in the south, a network of interconnected cracks, faults, and volcanic zones called the East African Rift System marks the boundary where the African continental plate is actively tearing itself into two separate pieces. To the west sits the much larger Nubian plate, carrying the bulk of the African continent. To the east sits the smaller Somali plate, carrying the Horn of Africa, a narrow strip of eastern coastline, and the island of Madagascar. A third plate, the Arabian plate, meets the other two in the northern part of this system, near the Afar region of Ethiopia, in one of the only places on the entire planet where three tectonic plates converge at what's called a triple junction. These three plates are slowly, steadily pulling apart from each other at a rate researchers have measured at somewhere around 0, 8 centimeters per year in the most active zones, roughly the speed a fingernail grows. That sounds trivial on a human timescale, and it is. Nobody's going to notice their morning commute getting longer because of it. But geological processes don't operate on human timescales, and a few millimeters a year, sustained continuously over millions of years, adds up to entire ocean basins. It's the same basic mechanism that originally separated South America from Africa, roughly 140 million years ago, carving out the Atlantic Ocean in the process, just caught this time at a much earlier stage. One researchers can actually observe directly rather than reconstruct after the fact from ancient rock layers. What makes the East African Rift System scientifically remarkable isn't just that it's splitting a continent, it's that it's the only place on Earth where this specific process, continental crust, actively stretching, thinning, and beginning the transition toward oceanic crust, can be studied in real time, on land, rather than pieced together from geological evidence millions of years after the fact. The crack that opened in 8 days. For most of the 20th century, this kind of continental rifting was assumed to be an almost imperceptibly slow process, unfolding over tens of millions of years without any single dramatic event marking meaningful progress. That assumption took a serious hit in 2005 in Ethiopia's Afar region, when the ground did something nobody studying the rift had actually witnessed happen so quickly before. Over the course of roughly 2 weeks, more than 400 earthquakes struck the Afar region in rapid succession. And by the time the seismic activity settled, a fissure roughly 60 kilometers long and up to 10 meters deep had torn open across the desert landscape. Researchers studying the event, including geoscientist Cynthia Ebinger of Tulane University, found that a rifting episode that geological models had previously assumed would require centuries to unfold had instead played out in a matter of days, driven by a combination of magma intrusion pushing up from below and the resulting stress fracturing the crust above it. The event forced a genuine rethink of how continental rifting actually proceeds, revealing that the process isn't necessarily the smooth, gradual creep the older models assumed, but can instead advance in sudden, dramatic bursts, punctuated episodes of rapid change, layered on top of the slower, steady background stretching. That 2005 event turned out to be more than a one-off curiosity. Subsequent research using satellite radar imaging has documented similar, if generally less dramatic, episodes of rapid deformation occurring elsewhere along the rift system in the years since, reinforcing the picture of a rift that advances through a genuine mix of slow, continuous stretching punctuated by sudden earthquake and volcanism, driven jumps forward rather than one smooth, predictable process, running at a single constant rate everywhere along its length. The most significant recent development in this story arrived in April 2025, when a research team examined a specific 500-kilometer stretch of the rift system called the Turkana Rift, running through northern Kenya and southern Ethiopia, and found it in a considerably more advanced stage of breakup than anyone had previously recognized. The team's approach involved analyzing existing seismic survey data, essentially measuring how acoustic waves bounce and travel through underground rock layers, combined with additional subsurface imaging, to build a detailed picture of exactly how thick the continental crust actually is at different points across the rift zone. What they found was striking. At the center of the Turkana Rift, the crust measures only around 13 kilometers thick, compared to more than 35 kilometers of crust at the undisturbed margins just outside the rift zone, a dramatic thinning that geologists specifically associate with a critical phase of continental breakup called necking. The term comes from a fairly intuitive physical analogy. Stretch a piece of taffy or dough, and it doesn't thin evenly along its entire length. It develops a narrow pinch section in the middle, a neck, where the material is considerably thinner than everywhere else, right before that narrow section eventually tears apart completely. Continental crust, under the right combination of tectonic stretching forces, behaves in a broadly similar way. And once crust in an active rift zone thins to below roughly 15 kilometers, researchers consider a continental breakup essentially inevitable, a threshold the Turkana Rift Center has now been confirmed to have already crossed. Christian Rowan, a geoscientist at Columbia University involved in the research, described the specific significance of the finding directly. Rifting in this particular zone had advanced considerably further, and the crust had thinned considerably more than researchers had previously recognized, placing Eastern Africa further along in the overall rifting process than the existing scientific consensus had assumed going into the study. Based on this evidence, the research team identified the Turkana Rift as the only currently known active rift anywhere in the world that has already entered this specific necking phase, the stage that immediately precedes actual ocean basin formation, making it, by the team's assessment, the most likely specific location where Africa's eventual split will actually initiate first. That discovery came with a genuinely significant revision to the expected timeline for when this process might actually complete, and it's worth being precise about exactly how much that timeline has shifted and why. Earlier estimates for full continental separation and new ocean basin formation across the East African Rift system had generally placed the timeline somewhere in the range of tens of millions of years out, a genuinely distant, almost abstractly slow prediction. More recent research, incorporating both the accelerated deformation observed in events like the 2005 Afar rifting episode and the newly confirmed advanced necking state of the Turkana Rift specifically, has compressed that estimate considerably. Cynthia Ebinger has specifically noted that researchers have reduced the expected time frame for full separation to somewhere around 1 million years, and potentially as little as half that, a genuinely dramatic revision downward from the tens of millions of years figure that had circulated for decades. It's worth being clear about what 1 million years, possibly half that, actually means in context, since it's easy to either dismiss it as functionally meaningless on a human timescale, or to accidentally overstate how imminent this actually is. 1 million years is still a genuinely enormous stretch of time by any human measure, dramatically longer than the entire span of recorded human history many times over. Nobody currently alive, nor their children, nor any descendants for hundreds of thousands of generations, will ever see this ocean basin actually fill with water. But on a geological timescale, where continental rifting has traditionally been discussed in tens of millions of years, a revised estimate measured in single-digit millions of years or less represents a genuinely dramatic acceleration, roughly an order of magnitude faster than researchers had previously assumed, which is exactly why this specific finding generated as much scientific attention as it did. The Turkana Rift study's authors were also careful to flag an important caveat that applies to continental rifting more broadly. Not every active rift zone on the planet actually completes the process and results in a fully separated landmass. Some rifting episodes stall out partway through, leaving behind a permanent geological scar, a deep valley or depression, without ever progressing to full crustal separation and new ocean formation. The specific significance of the necking phase identification in the Turkana Rift is that it represents genuine, confirmed physical evidence that this particular stretch of the rift system has progressed well past the stage where stalling is a likely outcome, making Eastern Africa's eventual separation considerably more probable in the research team's assessment than it would be for a rift zone that hadn't yet reached this specific advanced stage. What the rift actually looks like. Beneath the visible surface features of the rift, the dramatic escarpments, the chain of long, narrow lakes, the active volcanoes scattered along its length, researchers have also been mapping what's actually happening deeper in the Earth to drive this entire process, and that picture has gotten considerably more detailed in recent years as well. Research, led by earth scientists at the University of Southampton, has identified rhythmic pulses of molten rock rising up from deep within the mantle beneath Ethiopia's Afar region, a discovery that helps explain why volcanic and seismic activity across the rift tends to cluster in distinct episodes rather than proceeding as one smooth, continuous process. These deep mantle pulses appear to interact directly with the tectonic stretching forces already at work, periodically delivering it additional heat and pressure that both weakens the overlying crust further and helps drive events like the rapid 2005 AFAR Fissure Formation, essentially providing the deep Earth fuel source behind the more dramatic, episodic bursts of rifting activity observed at the surface. That combination of steady, grinding tectonics stretching alongside episodic, deep mantle-driven volcanic and seismic pulses is what ultimately produces the transition researchers expect to eventually complete the rift's transformation into a genuine ocean basin. Once the continental crust is thinned sufficiently, as it already has at the center of the Turkana Rift, magma from below begins rising directly into the resulting gap. And as that magma cools and solidifies, it forms entirely new oceanic crust, chemically and structurally distinct from the original continental crust surrounding it, physically welding the widening gap into what will eventually become an actual seafloor, where the water will actually come from. Once that new oceanic crust has formed across a wide enough stretch and the surrounding land has subsided low enough, researchers expect the final step to be relatively straightforward. Seawater flooding in from the adjoining ocean basins that already exist nearby. Given the East African Rift System's geography, running from the Red Sea in the north down through the Horn of Africa and into Mozambique in the south, researchers generally expect the eventual new ocean to be filled primarily by water intruding from the Indian Ocean in the south and potentially the Red Sea and Gulf of Aden in the north, gradually submerging the lowest lying sections of the Rift Valley as the surrounding crust continues to subside and widen. The geographic result, once this entire process eventually completes, would be a genuinely new coastline running down the eastern edge of what remains of the African continent, with the current Horn of Africa, including Somalia, Djibouti, and parts of Ethiopia and Kenya, along with Madagascar, effectively separated from the rest of the continent as an independent landmass, or a scattered cluster of landmasses, carried away from mainland Africa aboard the slowly departing Somali plate. Researchers have sometimes referred to the eventual result, once fully complete, as effectively becoming the planet's sixth ocean, joining the Pacific, Atlantic, Indian, Southern, and Arctic oceans as a genuinely new, named ocean basin on the map, though that framing, worth flagging directly, describes an outcome that remains at minimum hundreds of thousands to low millions of years away, even under the accelerated timeline the Turkana Rift research suggests. A rift sitting on top of human origins. There's a detail connected to this story that reaches well beyond geology, and it's part of why the Turkana Rift specifically has drawn so much scientific attention independent of the rifting research itself. The region sits directly on top of one of the most significant fossil-bearing landscapes in the entire study of human evolutionary history. The Turkana Rift and the surrounding volcanic terrain have yielded more than 1,200 documented hominin fossils, spanning roughly the past 4 million years, making the region one of the single richest sources of early human and human ancestor fossil evidence anywhere on the planet. That's not a coincidence, disconnected from the rifting process itself. The same volcanic activity driving the region's tectonic stretching has also, over millions of years, repeatedly buried and preserved fossil remains under layers of volcanic ash, while the active rifting has simultaneously exposed older rock layers at the surface through ongoing erosion and faulting, together creating an unusually favorable combination of preservation and accessibility that's made the region an exceptionally productive site for paleoanthropological research for decades. Researchers involved in the 2025 necking study specifically noted that the volcanic activity marking the onset of this advanced rifting phase, which the team's analysis suggests began roughly 4 million years ago, corresponds closely with the time frame covered by that dense hominin fossil record, meaning the same geological process now poised to eventually split the continent in two has also, over the preceding several million years, been directly responsible for preserving an unusually detailed physical record of human evolutionary history in the same location. Understanding the specific mechanics of the region's ongoing rifting, in other words, carries direct scientific value that extends considerably beyond simply predicting where a future ocean will eventually form. Why any of this actually matters. Right now, given that the most optimistic accelerated timeline still measures in hundreds of thousands to low millions of years, it's fair to ask why this research carries meaningful relevance beyond simple geological curiosity. The answer comes down to what the East African Rift actually represents scientifically. A live, observable, present-day example of exactly the process that has shaped Earth's ocean basins and continental arrangement throughout the planet's entire geological history, available for direct study in a way that's essentially unique on the planet's current surface. Every existing ocean basin, the Atlantic, the Indian Ocean, all of them, formed through fundamentally the same rifting and necking process now underway in East Africa, just completed many millions of years ago, leaving behind only the finished result for geologists to study and reverse engineer after the fact. The East African Rift offers something considerably rarer, a chance to directly observe and measure each individual stage of that process as it's actually happening, from the initial tectonic stretching through episodic volcanic and seismic bursts like the 2005 Afar event, through the crustal necking phase now confirmed in the Turkana Rift, providing researchers with genuinely direct present-day evidence for testing and refining the broader models used to understand how every other ocean basin on the planet originally formed. There's also a more immediate, practical dimension worth naming. The seismic and volcanic activity driving this entire process poses real, ongoing hazards to the millions of people currently living across the East African Rift region, an improved understanding of exactly how the rifting process advances, including where crustal thinning has progressed furthest and where future seismic or volcanic episodes are consequently most likely to concentrate, has direct value for regional hazard assessment and emergency planning, entirely independent of the multi-million-year question of when, or whether, the process eventually completes into a fully formed ocean. A continent still being written. What's actually happening beneath East Africa right now isn't a distant, abstract prediction confined to computer models and academic journals. It's an active, measurable, ongoing geological process, one that produced a 60-kilometer fissure in a matter of days back in 2005, one that's currently thinning crust beneath northern Kenya down to less than half the thickness found just a short distance away, and one that researchers have, within just the past year, had to substantially revise their timeline for, cutting decades of assumed waiting time down to a fraction of what was previously expected. Africa isn't going to visibly crack open next year, or in most of our lifetimes, or in the lifetimes of anyone currently living, but the geological machinery required to eventually split the continent in two and fill the resulting gap with an entirely new ocean isn't a hypothetical future possibility anymore. It's already running, right now, beneath the deserts and lake valleys of East Africa, in a landscape that happens to have also preserved in exquisite volcanic ash detail the deep history of the very species now watching it happen.